All right, I think we can get it started. So there are enough people in the list. So hello, everyone. My name is Makan Karger. Thank you so much for joining us today. So the IAG GNSS-IR working group is pleased to present its first seminar by Professor Felipe Geremia-Nievinski from the Federal University of Rio Grande do Sul in Brazil. So Felipe will be presenting a recent catastrophic flood in Brazil and their GNSS-IR experiment during this extreme event. So the talk will last around 40 to 45 minutes, followed by around 15 minutes for Q&A session. So I encourage the attendees to submit their questions into a Q&A box during the presentation. So if you would like to ask your questions directly to Felipe, please click the raise hand button after the seminar. So for those who have not subscribed to GNSS-IR working group mailing list yet, please do so if you are interested in receiving updates and advertisement announcement. So, all right, Felipe, the floor is yours. You're all eager to hear your presentation.
Thank you, Makan, for the introduction, and good morning, good afternoon, good evening to all the colleagues worldwide. This is a brief outline of my talk. I'll give you some of the geographic context about the catastrophe. Then I will describe the flooding event itself. And then we'll start in the technical part about the water level stations, both the conventional ones and the reflectometry stations. And then I will delve into the hydrodynamics that we have learned during this event. And I will complement with some satellite data sets, and I'll wrap up with some practical lessons from this exercise. So this event took place in the southernmost state in Brazil. It's the state of Rio Grande do Sul. And I would like to highlight some features. The main one is this huge coastal lagoon. It's the Patos Lagoon, and it's close to the ocean except for a small outlet at the south end. And up north, we have Guaíba. Most folks call it a lake, and we prefer to call it a river. And the reason will become more clear during this presentation. And on the right-hand side, on the top right-hand side, we see the city of Porto Alegre, the state capital. In the pink shades, there is a urbanized land where most of the population is in the north side of the city. That's unfortunately where the flood was the worst. And also in the north side, we have an archipelago, a fluvial archipelago. It's a confluence of four major rivers, and they end up in a braided system. Some colleagues call it a delta. We just like to call it a braided river. And then it empties into this Guaíba lake/river. And then focusing more at the bottom right figure, you can see the downtown neighborhood. And especially I would like to draw your attention to this narrowing, this constriction between this tip, that's the prison tip where it used to have a prison, and then there is an island right across from it. So all of the water from a huge water basin funnels through this 1 kilometer wide channel. So the flood itself was a result of a major precipitation during a 10-day period. We had more rain than what would be expected for several months. And this region naturally floods. The problem is there were people living here, and this is, you can see in red on the big map. We see the flooding region, and it covers most of the northern region of state capital, including major facilities such as the airport. The airport has been closed since May, so we are a multi-million metropolitan area without an airport at this point. And the flooding was not so severe in the south region, and we'll learn more about that in the data slides. And here on the bottom left, you see the plume. The water would carry a lot of sediment from the valley. In the valley region, the flooding was even worse. Water rose by tens of meters, and it simply devastated entire towns. But I will be focusing on the capital city because that's where we had at that time the GNSS-IR stations. And you see the sediment plume entering the Patos Lagoon very clearly here. Eventually, this would make its way into the ocean through the southern outlet. So this is Porto Alegre downtown. We have a GNSS-IR station right here in the middle. And here we can see, and there's, I would like to draw your attention to a flood wall that runs through this picture that was supposed to close the flow of waters. It's 3 meter deep above the terrain and 3 meter also into the ground to avoid water percolation. But unfortunately, the water found its way through this flood protection system and inundated this entire region. The flooded regions on the right-hand side, they were landfills created some 50 years ago, and now we can see the river sort of taking back the region that was artificially occupied. This is the main stream gauge that we had in the capital at that moment. It is run by the state government with help from the federal government. The city government didn't have any water level stations of their own, and this is unfortunately fairly common in Brazil, that city governments don't normally invest in water level monitoring infrastructure. They rely mostly on the state and federal governments, and stations get destroyed like this. It was built right by the water. As any conventional water level sensors, they need to be either into the water or just above the water. This was a radar type gauge, and they did not consider the maximum flood expected. The last one was in 1941, and everybody got relaxed and thought it would never happen again, and here we are. This picture was taken just a few hours before it got destroyed. And at that moment, I got a phone call saying that your sensor is the only one working in town, so make sure it runs. So I got a little bit nervous at that point, but I was confident only because I had more than one stations. And that's a critical lesson from this is redundancy. Every type of sensor has pros and cons, and we cannot rely on any single one. So let me take a step back and show some of the efforts that we have been carrying out for the past several years. In 2018, we set up a low-cost station right by this 5 meters away from this official gauge, because we wanted to compare, and not only the results were good, centimeter level accuracy, but we put out all the bill of materials and a build tutorial so that anyone interested could replicate it. So this is on GitHub. Most of you already know. If you don't, please go and look it up. If you have any questions, open an issue on GitHub. And at that time, we were using only GPS. Now we have GPS plus GLONASS, but it's still pending publishing. So, but if you need it, just shoot me an email and I can share the details. And at that point, we were starting to see some weird things about the official gauge, which is every time they would do some maintenance, they would shift the datum by a few centimeters up or down. And after some head scratching, what we realized is they had a ruler, a wooden ruler, that they would look at it and tune the radar gauge to match the ruler. So they would take an expensive and highly precise radar instrument, but the whole vertical reference was tied to a ruler that they would take a single or a few sites, and they would not be sit there and do a whole Van Castile type of testing for several hours. They would take only a quick site and then shift the radar type. So we started to see these up and downs in the official gauge, and that's only possible when you have redundancy. So here I stress again the take-home message: we need redundancy. Then shift 5 years later, we started building last year a telemetric network. So the previous one I showed you was offline version. So it would record the data in an SD card, and then you would go there every few months and download it. This was networked, so it would upload the data in near real time via cellular network. And VDS1 at the south was the first station, and then we installed the SPH4 in the north, and then IDP1 was finished during the flood event. And normally, no one would think it would be a good idea to establish 3 stations in the same lake. Remember, they call this a lake. It's supposed to be a level surface. And normally, yes, that's how it behaves. It's the water level is very homogeneous, but we got a big surprise during the flooding event. And please pay attention to the height of the antenna support. We always gave preference to poles and masts and towers, because we knew that that would give better observability from a GNSS-IR perspective. Remember, we needed the interference cycles to retrieve water level. So the higher the antenna is, the shorter satellite arcs we can use and more frequent altimeter retrievals we can have. And another point that was that paid good dividends was the ground survey. We always took a total station, an optical level, and reduce the height of the antenna to a local benchmark, and then this benchmark to the citywide network. So we were, it was nice to have the benchmark network in place from the city government. That was something that helped a lot because we didn't have to carry out long surveys, only from the antenna down to the benchmark that we set up around, and then a quick survey to the nearest benchmark. And that allowed us to compare water level at nearby stations and to infer water inclination or stream gradient. So this was the situation during the flood. One of the bitter lessons was the battery during a torrential precipitation event. It needed to be bigger. So we tried to make it as low cost as possible, but the lesson was you need to size your batteries to last at least 1 week, ideally 10 days, because during these nightmare events, there will be no sunshine for several days in a row. And at that point, we to keep it running, would ask for a ride to the Navy, to the firefighters, rescuers, and go and replace the battery. And now all the network has been upgraded with bigger batteries. So don't save on batteries. And here you also see the importance of having a tall monument, tall pole or tower. It gives you protection. And it was the critical reason why our stations lasted while the other ones failed. Okay, so this is the main data set. You see, we had two unusual large floods last year. That was kind of a warning. They were bigger than the biggest ones seen for the past several decades. And remember, we have in town a flood protection system. So the municipal government took a lot of criticism recently because they didn't do the proper maintenance in the flooding system. But there's more to that. And I will describe in a minute. And here on the right-hand side, you see the May 2014 event, a huge ascent from 1 meter to 5 meters. Well, this is huge in a floodplain environment like this. Topography is very mild, so every meter of water, it advances enormously in horizontal distance. As I said, up in the river valley, water was 10 times bigger in change, in relative, but it was because it was a narrow valley. Here it's a wide and flat floodplain. And I also would like to draw your attention to the fact the water levels, they lasted at this high level for several weeks, for more than a month. The 3-meter mark is what the authorities consider the flood level. It's on the port. When the wharf gets inundated, that's the 3-meter mark. And we were totally, as a population, not prepared to this duration of the flood. That took the hardest hit on the population. People would be away from home from several weeks. And here at the bottom, I overlay two of our stations, one in the north and one in the south. And there was a gap at the peak of the event. This gap was almost 1 meter. So 1 meter in about 1 meter water level difference in about 10 kilometers distance. In a water body called the lake, um, uh, so this explains why the northern region of the city was hit so hard. Because remember, there was this archipelago, it functioned as a sort of a sponge, and it retained the water, and water levels were naturally higher in the north than in the south, where the river was wider. So that was the first hint that we were seeing a dramatic stream gradient. And here we're talking about 15 centimeters per kilometer. So it can easily, it exceeded 2 meters from the south extreme to the north extreme of the city at the peak of the flood. Then we complemented the time series with maps. These are the SWOT maps. We were lucky to have it ready at the time we needed. It had been launched last year, if I'm not mistaken. And we were the first to show the extent of the stream gradient through the whole water body. And here in April, you see not only lower water levels, but you also see lower gradients. The water level difference between north and south sections, it was less than half a meter different. But during the flood, especially the peak, and we were also lucky to have a satellite pass the day after the peak, which was on May 5th. And in the whole archipelago region, and partially because of this constriction, not because of this constriction, it's a subtle but important point. It's the island system, the braided system that retained the water, and the constriction was a secondary effect. But whatever the reason, water levels were a few meters higher in the north region, where the airport sits, and where dikes and levees were built to protect the population. People were living right by a levee and they didn't know it. And here I will draw a profile through this a longitudinal line to show the water level elevation. Again, at the bottom in blue, we see the April conditions. Water was both lower and less inclined. And in the dots are our stations. We also run some conventional GNSS surveys on a boat, and those are the other points. And you notice the slope change at this point between point D and E, and this is exactly the constriction that I mentioned. So in the archipelago region, the stream gradient was higher than in the wider parts of the Guaíba system. Whenever there was a narrower channel, the water not only rose more, but it rose differentially more. So the gradient was larger. And this is all in a preprint we put together with all the SWOT and GNSS-IR and ground surveys. So this is the flood protection system that was in place. There was a flood wall running here in the north face of downtown. And then there were levees with, and the thing is, they used as roads. So most people wouldn't realize they were driving over a levee. And it was supposed to be between 6 and 7 meters high, right? And that would give a safety margin of about 1.25 meters above the last highest flood level that was observed in 1941. But for some reason, it was left incomplete and no one realized. And that was the major blow in the flood protection system. There was some leaks, etc. But compared to the fact that the levees were built 3 meters below what they were designed, so that was the major reason why this whole region, including the airport, got flooded. And again, as I take this to heart because I teach geodesy and surveying, and to learn that this whole event got worse because no one did the proper survey to see how it was built. And it was a problem of overconfidence. We all thought we were safe, and no one dared to check. So I sort of blame myself last year after the floods that we had. It would be easy to go and do a survey and see, hey, this levee is supposed to be 3 meters higher. But again, we all thought we were safe. And here the flooding regions, they match very well what was observed during the this year event. And another nice thing that we learned was the effect of this constriction. When you get so much water rushing through a narrow channel, what we observed, and this is not modeled, this is SWOT measurements validated with the GNSS-IR stations. We see a sort of a step, so it's continuity in the stream gradient. But it's not like you are going to see a waterfall here, but yes, there is a couple of decimeters difference, and it's almost as if the water is choked here. And this gains more relevance because when the government gauge station was destroyed, they moved it downstream. And they put it right here, just past the constriction, where there is a water drop. Not only there is the stream gradient, but there is also localized effect. And it didn't take much before we started to notice there was something wrong. And here at the top curve in blue is the official water levels reported by the government, and in the bottom one are variously our stations, our GNSS-IR stations, and in pink is where the government station was supposed to be. It was off, not by a few centimeters, it was off by 70 centimeters, by more than half a meter. And that was the amount of the water level difference between where the station originally was, which is sort of here, a little bit upstream, and where it was. So it was a 2-kilometer distance and a 70 centimeter water level offset during the peak of the flood. So when their station got destroyed, they built it downstream, rebuilt it downstream, but it was not possible to carry out the ground survey because everything was flooded. So they went with a boat and a ruler and said, well, it's 4.18 centimeters, the water level. Let's assume it's the same downstream. And then when the water started to lower, the gradient started to decrease, and the government station ended up hanging in the air. That's exactly what we see at the top. We try to warn them, say, hey, this doesn't look right. We have more than one station. In the stars, it was me and my students getting the feet wet and taking photographs because there were water level marks from the last great flood in 1941. And they were not pleased to hear the bad news. So at some point, they just started yelling at us, and I said, all right, I wash my hands. Let's give it time and see how it turns out. But then journalists, when the water came down, they started to realize, hey, wait a minute, the water is not as high as the government reports are saying. And then there was a big media spectacle. And well, the lesson here is do your ground surveys well. And if you cannot do it at the moment, do as soon as possible. And now, just 2 weeks ago, they finally released a report confirming this 70 centimeter offset. So, well, we told them, but we only knew it because we had more than one station. And that's the big lesson here. Redundancy is important. It's even in small distances. Remember, these stations are within 10 kilometers of each other, our small network. No one would purchase a network this dense. But after a major flooding event, you start to realize the hydrodynamics are more complex than we would like to think. All right, so now efforts after the event, with sponsorship from the Port Authority, we expanded the network, not away from the capital. So one station upstream, because all this water eventually comes down here. So if you get a good prediction in the river valley, a couple of days after you get that same water at the floodplain stations. And here in the river valley, the whole network was destroyed. And now they are rebuilding it. Then we had another station at the bottom, near the outlet. It's not quite by the ocean, but it's near. And that helped because, again, this region is very flat. So every couple of decimeters inundates large stretch of land. And here we helped the city government to run their evacuation maps. And the latest one is there's one at the limit between the Guaíba Lake/river and the big Patos Lagoon. And we have a nice view to both sides. And here it's a secondary constriction. And we also expect to see a smaller step in the water level. So hopefully we can do the stream gradient with a single station. And this is this is my new favorite station in the River Valley region. We built just in June. The city government was nervous because there was a flood forecast and they had no station at that moment. So we took the road and built a station in one morning. They were kind enough to set up this tall pole. So that's another lesson for us. If you ask, they build it for you. So we needed a tall, because here water level would go almost to that point, I think. This region was totally devastated. Entire neighborhoods with no house left, and then here is our antenna and solar panel and the electronics box, and here at the in August they did an exercise in which they opened the floodgates downstream, so the water level got lower at that point. It was a good. It seemed like an artifact, but it's real. Okay. And then they closed the floodgates and water goes back up. All right. So lessons that I can draw from this whole exercises: keep equipment as high as possible. Look for towers and poles, and if you don't see anything, ask for your local partners to build one if needed. And that's probably the main advantage of the technique that we are all working, right? I used to call it low cost, but now I just call it a remote sensor, because that's really the unique characteristic is we survive major flooding events if properly set up. Battery need to be at least 7 to 10 days. If you're doing a telemetry via cellular network, LTE or GSM, use a multi-operator, because at the peak of the flood, there was a blackout in downtown, and the cellular network went down for about a day, if I'm not mistaken. So some folks, they go for satellite telemetry, but then the costs skyrocket. We're looking at alternatives. You certainly need multiple GNSS systems. All our stations were GPS only, but when you're doing near real time, there were some windows in time that would not get a satellite rising or setting at the right azimuth, and people would start get nervous. In a major event like this, you start to get journalists calling, you start to get the mayor nervous. So at least GPS plus GLONASS you must for near real time, and if you can do Galileo and Beidou, that's nice too. That being said, the last 1 hour of data, the latest 1 hour of data, we didn't find it reliable. So we decided to discard. It's better to give no information than to give a false alarm. And it would ricochet up and down because there were so few data points. So try to be conservative in the latest few hours, and I would recommend discarding at least the latest 1 hour. So yes, it's not real time, but it's near real time. And when the conventional stations got destroyed, that's the best you can get. Do your best efforts to tie the antenna heights to the local net datum, or the regional or the national datum. Many communities, they have their rulers that they know the zero water level by heart. Here it's 3 meters. They know the flood has inundated the Port Wharf. So also connect to the local datums, because that facilitates communication. Save the raw data for future reprocessing. Here we say it's not a smart sensor, it's a dumb sensor, because the only job is to get the data out of the field as soon as possible. And then the smart part is done in the cloud. And we have tweaked the processing settings, and it was nice to have the raw SNR data to reprocess the whole time series. And whenever you find someone that is that is used to have the conventional water level technology, and my personal experience was they were kind of dismissive, like, well, we don't need GNSS-IR because we already have radars and hydrostatic probes and blah blah. Try to combat that with redundancy. So offer to set up a station next to their station, and when the worst happens, you can save the day. And also data density. The conventional water level gauge, they are they would never build with the density that we can afford with the GNSS-IR. Not only because the sensor is cheap, but mostly because the setup is easy. In a few hours, you hang the antenna and the electronic box and the solar panel, and you leave. You may return to do the ground survey, but there was you don't need to get your feet wet to start to install a GNSS-IR station, and that's a big difference. All right. So with that, I would like to thank all the students that have gone through hell with me in the past couple of months, keeping the network running. Colleagues, Christine for her GNSS ref package, Brazilian Navy for giving me a ride when we needed to replace a battery, and the Port Authority for sponsoring this. Thank you for your attention.
Yeah, thanks, Felipe, for such a valuable presentation. I appreciate the time you take to share with us your research funding. I really appreciate that. So it's fantastic to see that there are around 60 people joining in this session. All right, so we had a similar experience in Germany as well about the low-cost sensor that we had to install next to the existing conventional river gauges to show the results are reliable and to convince the people, the authority, that GNSS-IR is going to be useful. All right, so time to questions. Please raise your hand in case that you have questions so that I can allow you to talk. We have 3 questions here in Q&A box. Perhaps I can start with the first question. The first is that, are these any constraint on the height distance of GNSS antenna to the water body that should be observed? Is there any recommended height?
Well, a simple rule of thumb is 45 degrees, so at least as high as you are horizontally distant from the water. If you want the full answer, it's a little more complicated than that, but that's a useful rule of thumb. So if you are, um, say, 10 meters from the water, try to get at least, well, it's a rule of thumb. It has exceptions, but the deeper you get into the away from water, the higher you need to get. Maybe the ratio is not 1-to-1, but that's something to consider.
Okay, thanks. And the next question is from Ben Gutkenecht from Unibond. Do you have estimates or observation of elastic deformation due to water mass loading? Or was this considered in the data processing? So it's
Right.
asking about loading and PPP perhaps.
Well, our low-cost sensors, they don't save carrier phase, so we are unable to answer that. We are planning to set up a different geodetic monitoring network that does this sort of monitoring, especially in the archipelago region. It got so much sand that is whatever deformation occur, it might still have been in place. It might be permanent and not only elastic. But I don't have any estimates for that. I assume it shouldn't be more than a few decimeters, perhaps.
Mhm.
So all our water levels are relative.
Oh. All right. Okay. And there is another question. There are two questions from Jonathan. I think the second one is more relevant. How to perform GNSS-IR in real time? Is there no problem with this satellite orbits for post-processing? And we suffer very useful.
Right. So we use the Christine's package. We simply, well, it's a very simple near real-time processing. We simply reprocess the past 48 hours of data every half an hour. So as the new data files come in, we rerun it just the past 48 hours because sometimes the cellular network went down and some gaps were filled in. But you can just reprocess the last 12 hours and they were probably fine. Now
Oh.
with the orbits, that's something that we improved. We were using the elevation angle and azimuth that is provided in the data observation files in NMEA format, and then we cover the non-integer part. But especially for the TAL stations, we found a huge improvement in using the ephemeris data. And if you use the near real time or the ultra rapid products, you're probably fine. There were some tweaks needed because the ultra rapid product it didn't cover the entire period of time. There were some windows that were not covered by the ultra rapid product, so we had to replace the provider. We started using the Yuhan products.
So you recommend using the NMEA data, right? For orbits.
No, that's what we used to do, and then we had to stop using the NMEA elevation angles, and started reconstructing the satellite elevation angles, which again it's not an observable, right? It's something it's computed from the ephemeris in real time by the receiver itself, but then the NMEA format has a limitation that it puts out only an integer value. So we found it safer to discard the elevation angles in the NMEA and redo it using the ephemeris files.
All right. Okay, so thanks. So next question by Peng Feng. Thank you very much for the talk. Does the performance of GNSS-IR degrade in fast water level change?
Yes. So for coastal regions in large tidal range, we are all used to have to apply the vertical velocity correction, but we were surprised to have to apply the same for a river station, and especially in real time, it was nerve-wracking to see the water level curve taking off, and you get a few or more data points for each satellite arc, and then the curve is trying to go through that. And remember, the vertical velocity or the height rate is inferred from the water level measurements themselves. So you need to accumulate a few hours of data to get a reliable trend, and then apply the correction. All that the lesson that we got from that is you need to rerun the 48 hours, because sometimes data gets shifted up or down because of this vertical velocity correction.
Yeah, thanks. Next question by Surishi. He asked about what is the typical cost to transfer telemetry data for each station per year? How much does it cost?
So we collect the data at 1 hertz rate. We could lower the rate to maybe a sample once every 10 seconds, but and that would save some of the data telemetry. We also are using a more expensive multi-operator SIM chip. I don't have the figures right now, but I think it's around maybe $10 a month.
Yes.
My students take care of the hardware. I said I cannot take care of all of this, so can you do this for me? And then they build the hardware and they run the server, and I just look at the data. Otherwise, I would get insane.
We pay similar amount here in Germany, around €7 per month, which is not that much high. But an alternative, you mentioned that the telemetry, the cellular network was down during the flooding because the power was off. So
Yes.
an cheaper solution with respect to the satellite data transfer is a LoRaWAN that although it's not designed for very long, covering long range, but it can do a good job within a few kilometers for data transfer. So it can be an alternative for cellular network. So, all right. And we can ask 3 more questions. There is one more from Susilio. Are your low-cost sensor running near real time or just collect data? And I think you already answered these questions, right?
The data, the sensor collects data in 10-minute chunks, and then it closes a file. It doesn't stream like it's not M-trip. It It collects, it finishes a data file 10 meter long, and then it uploads to an FTP server. So, and then the server keeps looking at the data files and repeating the processing in real time.
Okay. Yep. And I see if there is any questions unanswered. Yeah, Laudi Yab asking about the cause of the huge flooding, the rise of the sea or the rainfall.
In this case, it was the rainfall. Well, very indirectly, there is the rise of the sea because of the whole global warming that pumps more water into the atmosphere, and the climate experts, they say these 100-year floods, they will get more frequent. So yeah.
All right. Okay, I think there are one last question, Felipe, do you have a most effective methods to reduce the power consumption? That's the last question.
Our power consumption is mostly from the modem that does the data transmission. The GPS is very low power. So transmitting in 10-meter batches is one strategy to reduce the power consumption, because you're doing in a fast way. Okay. You don't keep the modem turned on and transmitting, because here again we have two antennas, right? The GNSS antenna and then the GSM antenna, and it's the GSM one that takes the most power.
Yep. All right. I think we addressed all the questions. Felipe, thanks a lot. Yeah, I think it's 1 hour time slot is full. So before we closing the seminar today, so I would like to remind you that our next seminar will be given by Simon Williams in late October or early November. So I'll send around further details via the mailing list. So all right, thanks so much for joining us today. Thanks again, Felipe, for your presentation and sharing your story with us, and have a good day.
Well, thank you for the invitation, and hope to see you all again soon.
Yeah, bye-bye.